Hey guys, my name is IBM and I'm still taking you through our waves and superposition. And I think this is going to be lesson 11 where we shall talk about diffraction. I'll just be emphasizing the concepts of diffraction that you talked about in IGCSE. I'll just remind you of the course outline for AS Physics, which includes physical quantities and units, errors and uncertainties, treatment of uncertainties, kinematics, dynamics, force, density and pressure, work, energy and power, deformation of solids, waves and superposition, particle physics, electricity and DC circuits, and currently we are dealing with waves and superposition. So let's go to lesson 11, which is going to be diffraction, and it will be a very short lesson. So this is going to be a very short lesson because it is simply reminding us of the concepts that we studied in IGCSE about diffraction. So here we're just going to emphasize diffraction because it's going to be very important in our next step. We shall recall, we shall need to use the ideas of diffraction in interference and then the diffraction grating. But of course, I know that you talked about diffraction in your IGCSE in details. So let's go to diffraction. So when waves pass through a narrow gap or a narrow slit like the one demonstrated in this animation here, the waves tend to spread into what we call regions of geometrical shadow. In other words, these are regions for which the wave would not exist in case, or the regions where we would not expect the wave if it was not spread. For example, here I have a narrow opening somewhere here, and if the waves were not spread, we would not expect them to be in this region here, and we would not expect the waves to be in the other region there. So these regions where we would not expect the waves to reach, but they are reaching there, we call these regions of geometrical shadow. If the wave was just to continue in a straight line, it would just follow that middle part alone. So these regions here where the waves are spread to reach, we call them regions of geometrical shadow. So when waves pass through a narrow gap or a narrow slit, they spread out. And this is spreading. The spreading is what we call diffraction. So in IGCSE, you only define the diffraction as the spreading of waves. But you did not mention regions of geometrical shadow. Now that we know regions of geometrical shadow as those regions where the waves wouldn't reach if it was not to spread, the wave would not reach in that region if it was not to spread, then we are going to redefine diffraction in a more advanced way as the spreading of waves into regions of geometrical shadow. It is still spreading as you mentioned in IGCSE, but this time we introduce the concept of regions of geometrical shadow. Regions of geometrical shadow. So the spreading of waves into regions of geometrical shadow. When I talk about regions of geometrical shadow, these are regions where it would not be seen if it moved only in a straight lines or if it moved in a straight line. So this is only going to happen if the wave has passed through a narrow slit or a narrow gap, or it is passing or it passes by an edge. For example, diffraction cannot only be due to a narrow gap. We could have a barrier such as this one, and waves are instant or coming to the barrier, and after passing by the barrier, the waves tend to spread into regions of geometrical shadow. That's what you call diffraction in IGCSE. So spreading of waves into regions of geometrical shadow after passing through a narrow slit or past an edge. That is what we call diffraction. Your teacher in IGCSE must have emphasized that diffraction occurs with all waves, irrespective of their frequency or wavelength or speed. Diffraction occurs with all waves. In IGCSE, you also demonstrated diffraction using what we call a ripple tank, where you created a narrow slit or a narrow gap, and you produced parallel waves in a ripple tank, and these waves were seen to spread into regions of geometrical shadow. So diffraction can be demonstrated using a ripple tank, as you have seen here, or you saw in IGCSE. In your school, you should be having a ripple tank. So plane waves are generated using a vibrating bar and move towards a gap in a barrier as shown in this diagram here, Where the ripples strike the barrier, they are reflected back, and where they arrive at the gap, however, they pass through and spread out into the space beyond. So where they hit a barrier, they can be reflected back, but where they pass through a narrow gap, they spread into regions of geometrical shadow. They spread into the space beyond the narrow gap, and this is spreading out of waves that travel through a. It is this spreading out of waves as they travel through a gap or past the edge of a barrier that is what we call, or that is called, diffraction. So, diffraction is the spreading of waves into regions of geometrical shadow as they pass through a narrow gap or even as they pass past an edge. That is what we call diffraction. Now, the separation between the adjacent wavefronts, that is the distance between a crest and a crest or a trough and a trough, the separation between the adjacent wavefronts is what we call the wavelength in one of the lessons, perhaps lesson 2. So the separation between adjacent wavefronts of these waves is still wavelength of the ripples. And in IGCSE, you also might have mentioned that the easiest way to analyze these ripples is by using a stroboscope. A stroboscope would freeze these waves, or it would slow down the ripples for analysis so that we can measure the wavelength or the distance between the wavefronts using a stroboscope. So the separation between these waves could easily be measured if they were moving slow. Of course, in the laboratory, uh, the ripple tank may produce very fast waves, but in the presence of a stroboscope, in the presence of a stroboscope, of course, there is an illumination. This is supposed to be a lamp, I think. In the presence of the stroboscope, the waves are going to be freezed, and therefore they can easily be analyzed. We can draw the ripples on a screen at the bottom or below the ripple tank. We can measure the distance between the wavefronts, so that analysis can be done using a stroboscope. So a stroboscope is the instrument is what you never mention in IGCSE, but this is responsible for freezing these waves so that they can be analyzed. Now, this is going to be very important to think about in paper 5, that is planning and analysis in case a question involves analyzing waves in a ripple tank. So, the separation between adjacent wavefronts is called the wavelength, and this separation is very, very important because it determines the extent to which diffraction is going to occur. So, which factors affect diffraction? So the factors which affect diffraction, one of them is the wavelength. Diffraction depends on the wavelength, and diffraction depends on the size of the gap. So this diagram is going to help us understand or investigate the factors which affect diffraction. So the extent to which the ripples spread out, or the extent to which diffraction occurs, depends on the relationship between the wavelength of the waves and the width of the gap, or the size of the gap. Now look at the first diagram. The gap is very big, and look at the distance between the wavefronts, which is the wavelength. So here we notice that the wavelength is much smaller than the size of the gap. So the curvature of the waves is very small. They are almost straight, only curving at the extreme ends or at the edges. So here we say diffraction is smaller if the wavelength is much smaller than the size of the gap. In the second case, we have slightly decreased the size of the gap, but still the wavelength is still less than the size of the gap. So still there is more diffraction, at least the curvature here is more than the curvature in A, but the diffraction is still not as much pronounced as that which we would expect. In the second case, what is very special is that the size of the gap, this size of the gap is appreciably equal to the distance between the wavefronts, which is the same as the wavelength. So if the wavelength is equal, or approximately equal to the size of the gap, then diffraction is maximum. And of course, to show maximum diffraction, we don't even have the straight part of the curve, yet they were supposed to be incidentally straight, but is a perfect curvature. So here we said diffraction is maximum. So diffraction is maximum when the size of the gap is approximately the same as the wavelength. So in A, the width of the gap is very much greater than the wavelength, and there is hardly any noticeable, there is almost no noticeable diffraction when the gap is much larger than the wavelength. So there is no appreciable, or there is no visible, there is not enough diffraction when the size of the gap is much bigger than the wavelength. This is going to account for the reason as to why we cannot see someone who is just behind the door, even when the door is opened, simply because the wavelength of light is much smaller than the size of the door. When you look at B, the width of the gap is greater than the wavelength, and there is a limited diffraction too. But as the gap becomes narrower, the diffraction effect becomes more pronounced, the spreading becomes more pronounced, the curvature becomes more pronounced. And that's why in C, the gap width, or the aperture, is equal to the wavelength, and the diffraction effect is the greatest. How do we see that diffraction effect is greatest if the curvature is very perfect, almost a circle? So it means there's a relationship between the wavelength and the width of the gap as far as diffraction is concerned. I want you to note that the wavelength in all cases is remaining the same after diffraction. So the wavelength does not change. In other words, the distance between the crests, the troughs, the wavefronts, the distance between these wavefronts does not change. Only that the wavefronts just change the shape. In other words, in this case, they curve to show that there has been a diffraction, or to show that there is a spreading in this case. So the wavelength does not change when diffraction occurs. So diffraction is maximum when the size of the gap is appreciably equal to the wavelength of the wave. When the wavelength is much smaller than the size of the gap, the diffraction is almost not noticeable. That's why we cannot see someone behind the door, even if the door is opened, because the wavelength of light is much smaller. But we can hear someone behind the door, even when that is when the door is open, because the wavelength of sound is bigger. So let's try to explain several scenarios of diffraction that we never mentioned. IGCSE number 1, diffraction of sound waves. Remember, diffraction occurs with all waves, just like superposition does. Diffraction occurs with all waves, just like superposition occurs. And when diffraction occurs, the wavelength does not change. And because the wavelength does not change, yet the frequency of a wave depends on the source. If the frequency of a wave depends on the source and the wavelength does not change, it means the speed of the waves do not change when diffraction occurs. So nothing happens when diffraction occurs. Nothing changes when diffraction occurs because the wavelength does not change. And two, the frequency of the waves is depending on the source. So the frequency, if the source doesn't change its frequency, so the frequency of the waves also do not change. And from V equals to lambda F, it means that V also remains the same. So diffraction of sound waves. So the idea of sound waves bending around corners is not surprising at all. Of course, you can hear someone calling you when you are around a corner, because sound waves have a longer wavelengths and therefore can be easily diffracted even around relatively wide apertures, allowing the sound waves to spread beyond the corner. If I try to find the wavelength of sound from V over F, for an audible sound, V is of course the speed of sound in air is around 330, 340, and the frequency is for audible sound is around 100, let me just take 10,000. because the audible frequency is between 20 Hertz to 20,000 Hertz. So if I try to find this wavelength, 340 divided by 10,000, then I multiply this by 100. This is around 3.4 centimeters. This wavelength is big enough to undergo diffraction in a door of about 1 meter and so on and so forth. So at least we can hear the sound because the wavelength is very big. But we shall see what happens with light. So for example, you can talk quietly. That is, you talk slowly or not loudly to someone outside past an open door, and the person can hear you. So the opening is similar in width to the wavelengths of sound produced in normal speech and acts as a diffraction aperture. So I used a very large frequency, but most of the frequencies are less than this that we produce in most cases, even though our ears can detect frequencies between 20 to 20,000 hertz. We don't always produce all that range of frequencies. So the door opening is similar to the width of is similar in width to the wavelength of sound produced in normal speech, and therefore it acts as a diffraction aperture. So we can hear someone round the corner because the wavelength of sound waves is appreciably comparable or almost of the same order as the size of the gaps we experience or the sizes of the apertures we interact with in everyday life. How about when it comes to light? For light, I want you to recall the wavelength. You remember in the electromagnetic waves, we mentioned the visible light ranges from 7 times 10 to the power of minus 7 meters to 4 times 10 to the power of minus 7 meters in wavelength. So this was red and this is violet. So this wavelength is very, very small. In everyday life, we may not get such an aperture for light to go through so that we can notice the diffraction. So it means the wavelength is much smaller that we cannot come up with an aperture in everyday life where light will undergo diffraction and we see someone behind a corner, for example. So the suggestion that light waves curve around obstacles appears to contradict the obvious statement that light travels in a straight line, which in IGCSE you must have mentioned or must have called the rectilinear propagation of light. So all waves undergo diffraction, including light. But this idea of diffraction would make you think that we are contradicting the statement that light travels in a straight line, resulting into shadows. But when light or any other wave passes the edge of an obstacle, they curve. But this effect is small for light, especially when the gap size is much larger compared to the wavelength. So we cannot see someone around corners, or we cannot see around corners because light waves have a much shorter wavelength. The wavelength of light is of the order 10 to the power of negative 7 meters, and therefore light does not spread appreciably beyond their geographical shadows. So because the wavelength is much smaller, when light passes through an aperture, it doesn't spread much. It doesn't go far away. It doesn't spread far away from the aperture. So we get an impression as if light only travels in a straight line simply because of the smaller wavelength. So hence, diffraction effects are not usually noticeable or they are difficult to detect because the width of the gap is 1,000,000 times larger than the wavelength of light. So even if light is passing through, let's say, the smallest opening of 2 centimeters, this is still large because look at the wavelength. The wavelength of light is of the order 10 to the power of negative 7 meters, and 2 centimeters is about 0.02 meters. This value here is much bigger than this one here. So we cannot see behind a corner simply because light has a very smaller wavelength compared to the sizes of the apertures we interact with in everyday life. However, when laser light is directed onto a narrow slit whose width is comparable to the wavelength of the incident light, it spreads out to the interference patterns that we shall see in our next lesson. Even though we cannot easily see diffraction of light in our everyday life, but doesn't mean that light does not undergo diffraction. It is only not visible to us simply because in everyday life we don't have such smaller apertures for diffraction to be appreciable, for diffraction of light to be more pronounced. But in case we could have a very narrow slit, of course these narrow slits are not made manually, they are made using machines. Very narrow slits whose aperture is appreciable or is comparable to the wavelength of light, then light undergoes diffraction, resulting into what we shall call interference patterns in our next lesson. So, diffraction of light also occurs, and if it occurs with the light waves are part of the electromagnetic spectrum, so it means it also occurs with the radio and microwaves. Of course, diffraction with radio waves is very common. That's why we are able to listen to radios. Diffraction with microwaves is not very common because for them, they most of the times travel in a straight line. That's why they're not used for radio communication, but they're used for satellite communication. So, radio waves can have wavelengths of the order 0. Wavelength of radio waves is between 10 to the power of 4 up to around 0.3 meters. This is a large wavelength, so radio waves can easily undergo diffraction around apertures or between gaps because radio waves have a bigger wavelength. So radio waves can easily undergo diffraction because we can come up with large apertures for diffraction of radio waves to occur. These waves are easily diffracted by gaps in the hills and by the tall buildings around our towns and cities. That's why radio waves are used in radio communication. Microwaves, on the other hand, are used by the mobile phone network, have wavelengths of about 10 centimeters. 10 centimeters is about 0.1 meter. This is a relatively smaller wavelength. That is why they may not easily undergo diffraction. However, these waves are not easily diffracted because their wavelengths are much smaller than the dimensions of the gaps, and mostly they travel through space in straight lines. Of course, the wavelength is between 0.1 and I think it's around 10 to the power of minus 3 meters. So these are relatively smaller wavelengths, so such gaps would be extremely small. However, these ones are also used for communication by sending them in a perfect straight line to the satellite and back to the Earth. So cars need external radio areas because radio waves have wavelengths longer than the size of the windows, so they cannot diffract into the car. The wavelength of radio waves are longer than the size of the windows. Now this time we have a scenario where the wavelength is longer than the size or bigger than the size. So because the wavelength of radio waves may be bigger than the size, about 10 to the power of 4 meters, it means sometimes you may find some cars with antennas on the, let me say, there are some cars you will see. So this is a car, and then you will see that there is a long antenna on its bonnet like this. So some cars have these antennas here to pick the signals of the radios because radio waves can have since they have a longer wavelength, it again means the size of the windows for cars may be small, which also affects diffraction. Since diffraction is only maximum when the wavelength is equal to the size, not greater, not less. So sometimes cars have external radio areas or radio antennas to pick these radiations or these wavelengths or to pick these radio waves rather than relying on diffraction through windows. So if you try listening to a radio in a train without an external area, you'll find that the FM signals can be picked up weakly. Their wavelength is about 3 meters, but the AM signals with the longer wavelengths cannot get in it at all. So if you're in a train and you try to listen to a radio, if it is an FM radio, you will hear the signal, which is going to be relatively weak, because the frequencies used are around have a wavelength of about 3 meters. But the AM signals, which have an even longer wavelength in the radio frequency range, will not be picked because the train has no antenna or has no area to receive these signals. They have to rely on diffraction through the holes on the train. So that is diffraction. The takeaways from this lesson are just 2 or 3. Number 1, diffraction is the spreading of waves into regions of geometrical shadow when they pass through a narrow slit or past an edge or through a narrow gap. Number 2, diffraction is maximum when the wavelength of the waves is equal to the size of the gap or approximately the same as the size of the gap. We can hear someone around a corner, or we can talk to someone around a corner because sound waves have a longer wavelength. They can easily undergo diffraction. We can't see someone around a corner because light waves have a very short wavelength, and therefore there is no such a gap which would give a diffraction pattern that is appreciable or noticeable with light waves. Of course, we shall see that using narrow slits in interference, we shall see that using narrow slits we could produce interference patterns with light waves which are as a result of diffraction, but the slits should be very small. We have seen that radio waves can also undergo diffraction because of their longer wavelength. It means there are so many gaps in everyday life which can allow maximum diffraction with radio waves. Microwaves, on the other hand, have a relatively lower wavelength, and they may not easily undergo diffraction. Therefore, for them, they are basically used for satellite communication because they are sent direct to the satellite and sent direct back to the Earth from the satellite because they undergo less diffraction and mostly travel in a straight line, just like visual light. So that is diffraction. Those are the takeaways in diffraction for this level of AS, physics. See you in it will be lesson 12, where we shall introduce interference, two-source interference. Until next time, bye-bye.